there is something amiss in our understanding of the universe. Cosmology is at a critical juncture, grappling with one of its most fundamental questions. How fast is the universe expanding? For over a decade, two types of measurements have been in conflict. Observations of the current universe suggest that the rate of expansion, known as the Hubble constant, is approximately 9% faster than predictions based on data from the early universe. Scientists had hoped that the James Webb Space Telescope, the most advanced telescope ever built, would help resolve this issue once and for all. However, consensus remains elusive. Instead, the Space Observatory has reinforced this discrepancy with remarkably precise measurements, threatening to upend the standard model of cosmology. This new physics, which may need to either modify or even replace the 40-year-old theory, has sparked intense debate. An intriguing possibility is that there are aspects of the universe that we simply do not yet understand. Join us as we delve into how new ultra-deep images from the James Webb Telescope have confirmed that our comprehension of the universe is, indeed, flawed. Our universe began with a Big Bang. Energy, mass, and space surged into existence in an instant. Initially, a hot, expanding plasma of matter and antimatter particles formed. Theoretically, these particles should have annihilated each other upon contact. However, scientists believe that some unknown imbalance allowed for a greater quantity of matter to be produced, preventing the universe from collapsing in on itself. Gravity then compressed pockets of plasma, heating the matter so that sound waves, traveling at roughly half the speed of light, known as baryon acoustic oscillations, rippled across their surface. Meanwhile, the high-energy density of the early universe expanded spacetime, with some of this matter safely escaping the fiery conditions. As the universe expanded like a balloon, conventional matter that interacts with light coalesced around clusters of invisible dark matter, forming the first galaxies, interconnected by a vast cosmic web. Initially, as the universe's content spread out, its energy density and consequently its expansion rate decreased. However, around 5 billion years ago, galaxies began to recede at an increasingly rapid rate due to another mysterious force known as dark energy. The simplest and most well-known explanation for dark energy is that it acts as a cosmological constant, an inflationary energy that remains constant throughout space and time, woven into the expanding fabric of spacetime. Einstein referred to it as lambda in his theory of general relativity. As our universe expanded, the overall density of matter decreased while the density of dark energy remained steady, allowing dark energy to become the dominant force in the universe's expansion. When combined, the energy densities of ordinary matter, dark energy, and light establish the upper limit for the speed of the universe's expansion. These elements are also crucial components of the lambda cold dark matter, lambda CDM, model of cosmology, which describes the universe's evolution and predicts its fate, ultimately leading to a scenario known as the Big Freeze. Many predictions from the lambda CDM model have proven to be highly accurate. However, problems have begun to emerge. Despite extensive searching, astronomers remain in the dark about the true nature of dark matter and dark energy. According to Offer Lahoff, a professor of astronomy at University College London who is involved in cosmic surveys of dark energy, most scientists agree that the current composition of the universe is about 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we have little understanding of the latter two components. A significant challenge to the lambda CDM model has arisen, as measurements indicate the universe appears to be expanding at different rates. This discrepancy, known as the Hubble tension, suggests that depending on the methods employed by astrophysicists, the universe is expanding faster than predicted by the lambda CDM model. Those measurements have been verified through countless observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team that made the recent measurements using the James Webb Telescope, stated, "The only way I can understand this discrepancy is that the model we have between them might be missing something." Measuring the universe's expansion involves more than simply pointing a radar gun. The primary method utilizes the cosmic microwave background, CMB, a remnant of the universe's first light emitted just 380,000 years after the Big Bang. This cosmic imprint is observable across the entire sky and was designed to determine a Hubble constant with less than 1% uncertainty using the European Space Agency's Planck satellite between 2009 and 2013. In this vast cosmic image, the universe appears largely uniform, but hot and cold patches where matter is more or less dense reveal the presence of baryon acoustic oscillations, which formed as the universe expanded outward. This bubble-like structure eventually evolved into the cosmic web, a network of tangled strands where galaxies would form. By studying these waves, cosmologists estimated the amounts of ordinary matter, dark matter, and the value of the cosmological constant, or dark energy, resulting in a Hubble constant of approximately 67 kilometers per second per megaparsec. Let's pause to clarify this number. If a galaxy is 1 megaparsec away, it means that it is receding from us at a speed of 67 kilometers per second. If the distance increases to 20 megaparsecs, the recession speed rises to 1,340 kilometers per second and continues to increase dramatically beyond that. If a galaxy lies more than 4,175 megaparsecs away, it is moving away from us faster than the speed of light. A second method to determine this expansion rate involves observing pulsating stars known as Cepheid variables. These dying stars have outer layers of helium gas that expand and contract as they absorb and emit radiation, causing them to flicker periodically like distant beacons. In 1912, astronomer Henrietta Swan Leavitt discovered that the brighter a Cepheid variable is, the slower its pulsation, which allowed astronomers to measure a star's absolute brightness and thus calculate its distance. This groundbreaking discovery has been instrumental in understanding the scale of the universe. Dark matter, which interacts gravitationally but not electromagnetically, plays a crucial role in shaping the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. Despite extensive efforts to understand it, its exact nature and composition remain elusive, leading to ongoing searches through both direct and indirect detection methods. On the other hand, dark energy, responsible for the universe's accelerated expansion, presents an even more complex challenge. The standard cosmological model treats dark energy as a cosmological constant in its properties throughout spacetime. However, discrepancies like the Hubble tension suggest that dark energy's behavior may not be uniform. Alternative theories propose dynamic forms of dark energy that evolve over cosmic time, potentially affecting the universe's expansion rate differently at various epochs. Resolving these mysteries requires not only advanced observational capabilities, such as those provided by the James Webb Space Telescope, JWST, but also theoretical frameworks that can accommodate new data without discarding established achievements of the current model. Astrophysicists and cosmologists are exploring various theories, from modified gravity models to exotic particles and interactions beyond the standard model of particle physics. The implications of JWST's discoveries extend beyond cosmology into broader astrophysical questions, including the origins of life-supporting planets and the conditions necessary for complex chemistry to emerge in the universe. By studying distant galaxies and their environments, astronomers aim to gain insights into how Earth-like planets might form and evolve around other stars, shedding light on the prevalence and diversity of life in the universe. Looking ahead, JWST promises to continue pushing the boundaries of our cosmic knowledge. Its exceptional sensitivity and resolution will allow cosmologists to investigate the atmospheres of exoplanets, describe the properties of distant worlds in stunning detail, and explore the earliest chapters of cosmic history with unmatched precision. These efforts will not only deepen our understanding of the universe's past but also pave the way for groundbreaking discoveries that could reshape our understanding of physics, cosmology, and our place in the cosmos. As JWST enters its operational phase, cosmologists eagerly await new insights into some of the universe's most profound mysteries, whether it's unraveling the nature of dark matter and dark energy, understanding the formation and evolution of galaxies, or exploring the potential for life beyond Earth. JWST is poised to transform our comprehension of the universe in ways that were once thought impossible. In conclusion, the convergence of cutting-edge technology, theoretical advancements, and comprehensive observations heralds an exciting era in cosmology and astronomy. JWST's contributions are expected to be pivotal, offering a clearer view into the universe's earliest moments while testing and refining our foundational theories of its structure and evolution. As we embark on this journey of discovery, the secrets of the universe await exploration, with JWST at the forefront, ready to unveil the mysteries of our vast origins and destiny. By transforming Cepheid variable stars into reliable standards for measuring the vastness of the universe, cosmologists can construct a distance ladder. This method enables them to step back in time, progressing through different epochs of cosmic history. This distance ladder is one of the most dependable tools astronomers have for estimating cosmic distances. To establish the first rung of this ladder, astronomers select nearby Cepheids and cross-check their distances based on their pulsating light, which can be calculated. Wendy Friedman, an astrophysicist at the University of Chicago, explains that subsequent rungs are added using measurements from these Cepheids. Researchers then examine the distances of stars and supernovae at each rung, analyzing the extent to which their light has been redshifted to longer, redder wavelengths as the universe expands. This process provides an accurate measurement of the Hubble constant. In 2019, this method was employed by Adam Rees and his team, who focused on the Large Magellanic Cloud, one of the Milky Way's closest neighbors, using the Hubble Space Telescope. Their findings were surprising, revealing a remarkably high expansion rate of 74 kilometers per second per megaparsec, which stands in stark contrast to other estimates. However, Hubble's limitations in precision, especially in densely packed regions of space, caused some distant Cepheids to blend into neighboring stars, leading some cosmologists to argue that the result might stem from measurement errors. With the launch of the James Webb Space Telescope, JWST, in December 2021, the scientific community anticipated either a resolution to this discrepancy or further confirmation of it. With a mirror 6.5 meters wide, almost 3 times larger than Hubble's 2.4-meter mirror, JWST can detect objects that are fainter than anything Hubble could observe and is significantly more sensitive in the infrared spectrum. This capability allows JWST to explore a broader range of wavelengths. By examining Cepheids observed by JWST in the galaxy NGC 4258, along with bright Type Ia supernovae, another standard candle since they all explode at the same intrinsic brightness, Rees and his team arrived at a nearly identical result of 73 kilometers per second per megaparsec. Other measurements, including one by Friedman using Hubble on the brightening of red giant stars and another that analyzed light bent by the gravity of massive galaxies, produced values of 69.6 and 66.6 kilometers per second per megaparsec, respectively. Another approach utilizing gravitational lensing yielded a result of 73 kilometers per second per megaparsec. Cosmologists were left reeling. Ronan Kai, a cosmologist at the University of California, Merced, noted that while the cosmic microwave background (CMB) temperature is measured with 1% accuracy, the Cepheid distance ladder measurement is approaching that level of precision. A difference of just 7 kilometers per second, although seemingly small, is unlikely to be a mere coincidence, suggesting the need for a deeper explanation. The recent outcomes have further complicated the understanding of cosmology, dividing researchers into groups pursuing vastly different solutions. Following the Hubble results, an official attempt to resolve the discrepancies at a 2019 meeting at the Kavli Institute for Theoretical Physics in California only heightened frustrations. As the late Vera Rubin, who provided evidence for dark matter, remarked, no one wanted to abandon their findings. Each scientist strongly believed in the accuracy of their observations, leading to a collective desire to reconcile these differences. In February 2023, as JWST and another independent Hubble distance ladder measurement reaffirmed the Hubble tension, cosmologists were faced with 3 possible explanations: measurement errors, new physics, or a combination of both. Kai explained that most of the data supports the idea of new physics. The simplest and most widely accepted theory posits that dark energy behaves differently today than it did in the early universe. If dark energy was stronger in the past and has since diminished, it could make the universe appear smaller in retrospective observations, resulting in a faster apparent expansion rate. Other theories suggest the possibility of 2 types of dark energy or interactions between dark matter and light. However, these theories introduce complexities that cosmologists are cautious about without further data. Dark energy and dark matter are not the only mysteries JWST is helping to unravel. Upon its launch, JWST was tasked with observing the universe further back in time than any previous telescope. Its revolutionary imaging technology enabled it to view galaxies formed just 300 million years after the Big Bang. Yet, while investigating the universe's origins, cosmologists discovered that these early-stage galaxies are significantly larger and more developed than traditional models predict. According to standard models, early galaxies should be filled with young, hot stars forming at a rapid pace. However, JWST revealed that many of these galaxies are rich in heavy elements from previous generations of stars and possess rapidly forming massive black hole cores. JWST's observations have intensified the ongoing debate in cosmology by providing precise data that both confirms existing inconsistencies and unveils surprising insights about early galaxies. Addressing the Hubble tension and comprehending these early galaxies may require new physics or a substantial revision of the standard cosmological model. The quest for answers represents one of the most exciting frontiers in contemporary astronomy. JWST has not only transformed our understanding of early galaxies but also opened new avenues for exploring fundamental questions in cosmology. Its infrared capabilities allow it to delve deeper into the universe than ever before, capturing light from some of the earliest galaxies formed merely 300 million years after the Big Bang. These discoveries challenge the traditional view of galaxy formation, suggesting that early galaxies were not simple, youthful structures but rather complex systems rich in heavy elements and hosting supermassive black holes at their cores. This disparity between theoretical predictions and observational data raises critical questions about the processes driving galaxy evolution in the early universe, hinting at mechanisms that may have been more rapid and efficient than previously assumed.